If everybody would please, let's go ahead and put this data into your calculator. XY, we're looking at, list 1, list 2. It's age and range of motion, can't talk, because what I want to get into is the standard error. That's the left where we left off. So we haven't talked about standard error, which is the standard deviation of the residuals. So let's get that data set in, and then we'll go from there. Data in. Go ahead and set everything up. Linear regression, scatter plot with the line in it. Make sure you can do that. Okay. Line looks really good. I'm going to readjust my window. I'm probably going to go, I'll go from 50, 75. I'll scale it by 5s. Climb in, going to make that 100. Max, going to make that 180. I'm going to scale that by 10s. Okay. Does your data match my data? No, if it doesn't, we're in trouble. This point, things you should be familiar with, things you're able to do. There's your linear regression model. You should be able to find your line of best fit by using A plus BX. You should also be able to find R and interpret it in context. You should also be able to look at slope, put that in context, and the y-intercept if necessary in the context. Next thing I want to do is show you a prediction. I would like to make my prediction at, say, x equals, what was this, range of motion and age. I want a prediction for a 64-year-old. I know that I have a data piece that's 64,131. That's my actual data piece. If I want to get my prediction for a 61-year-old person, did I say 61? 64. Here's what you want to do, and I think I showed you guys at the tail end yesterday. Press second, calc, and then value. And you want the value when x equals 64. If you hit enter, it will plug that into the linear regression model for you, and it will give you the expected value or the predicted value. Again, that is second trace, which says calc. And you want it to calculate a value. It's going to say x equals what? Where do you want me to calculate the value at? Now I'm going to do it for a 70-year-old. X equals 70. It will predict a value of 153.5155. And that's what happens when you plug in a value of x equals 70 into your linear regression model. Okay? It's an easy way without having to do it by hand. All right. Next thing I want you guys to do, press stat, hit edit again. You should have that in list 1 and list 2. Go up and hit list 3, where it says list 3 equals. And here's a nice little button for you. Press second list. Go back to the one that says resid. So have this 3 equal the residuals. And there you have all your residuals. Again, watch, I will clear out list 3. List 3 is naked. Press second stat, which gets you to your lists. You should have a list, I think it's 8, that says resid. After residuals. So list 3 equals your residuals. Hit enter, and it will be your residuals.
I got errors. Yeah, I got errors.
You need to rerun linear regression. So stat, calc, 8, run your linear regression. Now that is stored in your calculator. Hit stat, edit, go into list 3. List 3 equals your residuals. And you should get it. Okay. Now, this next idea is, I would say, one of the most advanced ideas that we're going to look at statistically to this point in this class. So I want you to follow along with me and try to see how it connects. Okay? Because we're talking about, I don't want that one. This one. We're talking about a linear model here. Okay? And one thing that you guys have heard me talk about is this is just a prediction. And we've said if it's a good predictive model, then some of the times it will underpredict, some of the times it will overpredict, and that difference between the actual value and the predicted value, that's a residual. And one of the other things I told you, when you're looking at the residual plot, we like to have no patterns in that residual plot. We kind of like to make it be a mess. Residual plot is messy. That's good. Here's what that means. And here's the thought connection. If my residual, the distance or the value from my actual data piece and my predicted data piece, if that is random, that means I can not know whether I'm over or under predicting, but it means I'm going to be close. Are we okay with that for good predictive model? In fact, if my residuals are random, then that means at any given, any given data point, there's my expected or my predicted, and I may or may not have a data piece that's there. I might have 3 data pieces that are there. Because when you guys are going to find out you're going to do your experiment, I know somebody's doing something about arm biceps. Well, you may have 3 guys that have the same arm bicep. That's the same X value, but they may have different Y values. So you may have 3 or 4 data pieces on one X value. Do you agree that that would have 3 or 4 different residual values? Does that make sense? Okay. If your residual is scattered, then at any given coordinate, we could have an actual data piece above or below. But where that data piece is, the actual data piece is random. Does that make sense? And if that data piece is random based on our residual plot, then any given data piece will behave like a normal distribution. In other words, we can now talk about how far away we would be from normal if we had a mean and a standard deviation. You guys remember the mean and standard deviation? 68, 95, 99. You guys remember that normal curve? I said it's a big deal. Get it back in. It's going to come back into play. Okay? It's kind of about what we're about here. So what happens is I need to find the standard deviation, the standard error, about how far away any data piece is from that predicted data piece. And when I have a random residual plot, I can apply this normal curve. Okay? So next thing is, how do you find a standard deviation? Well, the thing that we're talking about is our residuals. Okay? Here's how you find it. That's the wrong one. I keep opening the wrong slide. Standard deviation of the residuals is what I'm calling standard error. And we calculate the standard error this way. And what it is the standard deviations of our residuals. The square root of this divided by n minus 2. SS resid stands for the sum of the squares of the residuals. Okay? The sum of the squares of the residuals. I will tell you that I won't have you calculate this by hand. I just want to point out, well, today we're going to calculate by hand, but that's going to be the only day that we're going to do it. Because I want to look at where it's coming from, where the standard deviation is coming from. It's coming from our residuals. So that's the sum of the squares of our residuals divided by n minus 2 square rooted. Okay? Normally, it will be reported to you. You just need to be able to interpret it and know what it's talking about. Okay? So, where's that at? Again, if you see the picture that I'm hopefully painting, it will very much help you interpret what standard error is. And that's the thing that I'm going to expect you to be able to do. Interpret standard error. Since we have this nice random residual plot, no patterns, the distribution of my residuals is random. Since the distribution is random, I can calculate the standard deviation of my residuals, and then I can apply the normal curve across any given point on that line. And I'm going to give you a sentence to interpret that. So, how do we do this? Like I said, it's going to be reported to you, or I'll give it to you, and I'll ask you to interpret. I really want to ask you to calculate it. Just want to show you where it's coming from. To do it in your calc, that's the sum of the squares of the residuals. Sum of the squares of the residuals. Well, I have my residuals in list 3. You guys should also have your residuals in list 3. If you're going to do the sum of the squares of the residuals, what I'm going to do in list 4 is square my residuals. And I can just do that by saying list 3 square. Do you agree that's squaring my residuals? There is my residual square. And now I need the sum of the squares. The reason that we are squaring this is because, again, I'm talking about variability. How far away on average is an actual data point to my predicted data point? That's what we're all about with linear regression. How far away are we from predictions? Because how good is the predictive model? That's what I'm tasking you with in your problem. I want you to find out a good linear model. Bad linear models don't help us. Right? So, if we were, do we agree that in list 3 that's our residuals? That's above and below. Right? We have positive and negative values. Now watch what happens real quick if I sum list 3. If I'd like to get a typical deviation, how far above and how far below, when I sum list 3 right now, and I'll show you this in a sec, when I sum list 3, something funny happens. That's 7 times 10 to the negative 11. Once for scientific notation, that's really, really close to 0. In other words, when I look at my residuals, I have just as much above and below. That should make sense if I'm talking about a predictive model. Some of the times I'm going to overpredict, some of the time I'm going to underpredict, but on average I'm going to be close to it. Well, that doesn't do me any good if I'm trying to find the average, because I take that 0 and divide it by how many data points I have, and that would be how far away on average I'm deviated from my line of best fit. Does that make sense? But if I take 0 and divide it by any number, I'm still going to get 0. So that's the reason we square it. Because when you square a number, a negative times a negative becomes positive, and a positive times a positive is positive. So we're summing the squares, just like we did back in standard deviation. We're summing the squares of the residuals. So here's how you're going to sum the squares. You're going to hit second, stat, go over to math, and there's one of the buttons that says sum. We're going to press 5, and we want the sum of the squares. So for us, it's in list 4. That's the sum of the squares of our residuals. By the way, you can also do this. Math, sum, resid, squared. Oops, I didn't do something right there. I have to rerun mine. Oh, thanks. What do I got to do? Start it again. Sum, list, resid, squared. There we go. There you go. Same. Should match. Okay? Do we agree that we've got the sum of the squares of the residuals now? Calculator does it all. As I told you in this class, calculator's going to do all the work for you. You need to know what it's doing. We're going to divide this by n minus 2. That's our formula. N minus 2 is the number of data pieces. I think in this one we got 2, 4, 6, 8, 10, 12, 14, 15. Is that right? 15 data pieces. 15 minus 2 is 13. And at the very end, we're going to square root it. So that is our standard error. Rounded to 4 decimal places, 1.6671. Now, how does this match? Why is this valuable? Here's the application. If I have this predictive model, I am going to, when I plug it into our formula, it is going to predict some value here. Does that make sense? We have a y equals a plus bx for this problem. You can't remember what it was. Negative 98.235 plus 3.5964x. Something like that. And if I want to predict the value at, say, and we've done that already, if I wanted to predict the value at, what did we pick, 64, when I plugged 64 in, I can't remember what it was. It's really close to 130, I think it was, 131. I don't remember. I may or may not have data pieces there. That's my predictive model. But if I have my data piece there, then I know that on average, or within one standard deviation, 68% of the time I would capture that data piece. So adding 1.6671 to 131 would get to that standard deviation. Subtracting it would get you to that standard deviation. It tells you a range of where your data should fall. We know 95 is within 2 standard deviations, and then 99 is within the 3 standard deviations. So that should be able to put into context. In fact, if I'm looking at this predictive model, if it spit out at 64 a value of 131, then I can say 99% of the time, if I found, and I don't know what 3 times 1.6 is, it's like 4.75 or something like that. I don't know. About 4.7, we'll call that. I take 131 plus 4.7, 131 minus 4.7, and do you agree that that would be 3 standard deviations above and below? And if I have 3 standard deviations above and below, 99.7% of the time, I should capture that data piece. Does that idea make sense? Okay? And that's what we're connecting. And that's where we're going. It's a really hard abstract idea to see. We'll continue to build on it and continue to build on it. So this number, interpreted, which is what I do expect you to be able to do. The standard error is the typical amount by watch and observation. And observation, I'm really talking about the actual data piece there. Observation deviates from the least squares regression line. Okay? Again, we know if our residual plot is nice and messy, no discernible patterns, then I can find my standard error because my distribution is random. We'll call that normal. Then I calculate that. I can apply that normal distribution rule. It's the average amount, typical amount, by which an actual data piece, if it exists there, does deviate from that least squares regression line. Remember, least squares regression line vocab-wise, that is our line of best fit. It's what we've done. Y hat equals. Okay? This will come back into play later on. Second half of the course, standard error, slope, that's where it's showing up on the AP exam. So I will table this idea for about, 3 months here. We'll revisit. I'll say, hey, remember when we talked about this long ago in a galaxy far, far away? You'd be like, no, Mr. Wood, I don't remember it. But at that point, you probably will recall it pretty quickly because you're going to have a lot more understanding about this variability piece as we move forward. All right. Next part. Coefficient of determination. I already told you, hey, this is the other thing. We've flirted with it at this point. If you haven't figured it out yet, it's R squared. Okay? R squared. It's coefficient of determination. The way I remember coefficient of determination is another interpretation. I would make an index card on this. And this is kind of the way I look at it. R squared is always interpreted as a percent. Okay? And for coefficient of determination, this is the way I remember the interpretation of it. Remember, I gave you a way to remember how to interpret slope. You should have a way to how to interpret R at this point. It's the same thing every time. It's the same thing every time. For coefficient of determination, I call it silly slope. Coefficient of determination is silly slope. I go like this. Change in y over change in x plus y. Silly slope. It's not an equation for slope. It just looks like an equation for slope. Remember, delta means change. Okay? In this problem we're talking about, y was range of motion, and x was age. Okay. I'm going to put it like that. That's just my context. Matching the context with my silly slope. Does that make sense? Again, I know that's not the slope formula. It's just the way I remember this interpretation. On this problem, I don't remember what R squared was. Looks like I got to rerun it. R squared, 0.9901. Okay? So in this case, we're going to say R squared squared is going to be 99% of the, and this is change. Delta is change. I'm going to use the word variation here. Okay? 99% of the variation in range of motion that can be explained by the, and the next piece I'm going to use, again, variation in range of motion, that's this part here. Variation in range of motion that can be explained by, I'm actually going to use this division sign, it means division. I'm using it to remember the word line because it's a line that can be explained by the linear relationship between age and range of motion. Okay? The change in y from the linear relationship. Okay? That's your interpretation. It's going to be the same thing every time. It's going to be the percent, whatever r squared, of the variation in whatever your y is. That can be explained by the linear relationship. That will be the same every time between whatever x is and y is. So there's your interpretation of r squared. This one's the coefficient of determination. Another way that can help you, if you look at it, can be explained by, can be determined by. Coefficient of determination, change in y can be determined by the change in x and y. Try to see how it connects, because memorizing these things, they're so close in their interpretations. R squared, standard air, and R. Okay? They're all different. They're all describing how good of a fit that line is. Okay? Last piece I want us to do. By the way, with this data set, I want to go back to, actually, it's not here. See. With this data set, how many people noticed it's actually not a very good fit? Anybody notice that? In fact, I want to look at the residual plot here. Now, our r squared value, excellent. Our r value here, excellent. Our visual assessment of the line, excellent. Okay? Now, look at the residual plot, because that's the other thing that we use to determine how good a line is as a predictive model. Do the residual plot of this data, and you can either name it residuals, or I think your residuals, you guys, it's list 3, right? So you can change that to list 3, or you can name it the resids. And I don't know what you got. But I do want to look at that residual plot. You're going to have to zoom stat that. And now, that is a very obvious pattern in the residual plot. And I said that's a big red flag when we're analyzing line of fit. When you have a discernible pattern, notice what happens here. Is that over or under prediction? Under prediction. It consistently underpredicts in this range. It consistently overpredicts in this range. Consistently underpredicts in that range. That is definitely a discernible pattern. So when we see a pattern like this in the residual plot, all you need to say is a nonlinear model will be better. That's all you need. In this case, if you look at that original data set, in terms of a nonlinear model, let me get that data set back up here. if you look at it, a line won't be that great. We'd actually like to have a curve that fits that data. Does that make sense? There's plenty of different curves, depending on what level of math you got to. Algebra 2, pre-calc, calc, there's plenty of different curves that we can use to model to match that. Whether it be logarithmic, whether it be exponential, whether it be quadratic, whether it be cubic. Because again, we only are going to use that curve to make predictions about that data set. And if you guys remember about curves, cubics, they don't even look like this. They might tail down here. Logs don't even look like that. We've got asymptotes. We've got all sorts of things happening. We're only concerned with the model from where our data is. And that's what you need to say. A nonlinear model is better. Okay? Last part, you won't see so much about this. In fact, what I want to do is keep the data set that we already have. I want to do a transformation of this data, because it's the other thing they may ask you to do. In fact, I'm asking you guys to do it on the project. And what might we do? We want to kind of norm that data a little bit. In this case, what I want to do, I will. That's a big range. We'll get a new data set in here. Actually, let's go ahead and put a new data set up. I want you guys to put this data set into your calc. Okay. So I'll give you a second for that. Hi, people. Does yours match mine? Yes? What's that?
Yeah.
Oh, you guys still need to finish entering your data? Sorry. Go ahead.
No.
Now, do you guys match me? Hopefully you can say on visual inspection, linear model's not good.
It looks like the best thing ever.
It looks like the best thing ever. You and I need to have a chat of what the best thing ever is. Not that. All right. So, running linear regression there. What we're going to do, I think you'll also agree, ugly R values. Although my R value here is a moderate linear relationship, negative, right? Okay. So, here's what we're going to do. When you have a data set like this, you may manipulate your data. Remember, I'm not going to right now, I'm not going to trim anything. And you can't just change your data with an eraser and change it into something you like. I think we've covered that in this class. However, you can do something to this data to help make it more linear. In this case, I am going to take the log of my x values. Okay? I want to take the log of my x values only. So over there on list 3, I'm going to log my x values. How do I do that? Press log list 1. So I've now taken a log of my x values. Now, notice that I haven't erased any data pieces here. All I've done is corrected or tried to manipulate my data in order to get it more linear. And you're allowed to manipulate data. You can square root your data. You can square your data. You can take the natural log of it. You can raise it to the power of e. You can do whatever you want as long as you're consistent. Have I done the same thing every time in list 3 to every single data piece I have? Yes. Okay. So now what I want to do is I want to run linear regression on my transformed data. To run linear regression on my transformed data, stat calc. Now, the new x values I want to use are in which list? They are in list 3. So I need to tell my calculator to run linear regression on list 3 And then I'm keeping my y values the same, so that is in list 2. Does that make sense? I've transformed my x values. I log every single x value I had. And then we're going to go to, I'm going to go ahead and get that new line. And then I'll pull up the scatter plot in just a sec. But what do you notice about our new r values? Did my linear model got a lot better, didn't it? And I logged the x values. So let's look at that scatter plot. What do I need to do? I need to zoom stat, right? No. I need to change my scatter plot. Because my x list is where? List 3. And now, zoom stat. Do we have a better linear model here? Was it better than before? Okay. Did it help straighten that line out a little bit from our data? Is it perfect? No. Is our residual plot still going to have some patterns in it? Probably. Can I help clarify before we move forward? What?
We're trying to figure it out.
All right. I'll give you guys another chance to practice. This is a transformation. Do we agree with this transformation? All we've done is log the x values. Do we also agree that it's not quite great? Here's what I want you to do. Log the y values and rerun your linear regression with the log of x and the log of y. Show me in your calc that scatter plot and that new linear regression and those r values. So, okay, I want you to transform it more. This was just a transformation of x. Now I want a transformation of log x and log y. So do that and show me your output. I want to see that. For your project in your textbook, it tells you different kinds of transformations you can do. For your data set that you come up with, you're welcome to manipulate it any way you want. What I'm concerned with on your project, you choose a way to manipulate your data. That doesn't mean erase data pieces you don't like. It means transform your x values, transform your y values, transform only the y's, transform only the x's. It doesn't matter what you choose to do. Pick a model of transformation that you like. And you might experiment with a bunch of them because odds are you're probably going to have your data in your lists on your calc. So it's very easy to manipulate it. What I want is analysis of it in your project. Here's my actual data set with my actual analysis. Here's my transformed data set with its analysis. The better linear model of the two is blank because blank, blank, blank. Does that make sense? Any questions about what I'm looking for the project and the transformation part of the project? Okay? All right. That's it. Of course, I went long, so how long did we go? 39? Assignment.